Ever wonder what's really happening when a piece of iron rusts, a log burns, or even when you bake a cake? It's all chemistry, my friend. Today, we're going to dive into the absolute fundamentals, chemical reactions and equations. We'll break this core science chapter down and show you how it's happening all around you, probably right now.
So, here's our game plan for today. First, we'll look at the changes we see every day. Then, we're going to learn the special language chemists use to talk about them. After that, we'll figure out how to balance the chemical books, meet 6 different types of reactions, and finally, see how all this stuff plays out in our actual lives. Let's get right into it.
All right, let's kick things off with Section 1. The world around us is constantly in motion. It's always changing. But, not all changes are created equal.
Okay, so check this out. You've got 2 basic kinds of change. On the left, a physical change, like ice melting into water. It's still H2O, right? It's just in a different form. You can freeze it right back into ice. It's totally reversible. But then on the right, you have a chemical change, a rusty nail. Here, the iron has actually bonded with oxygen to become a whole new substance. You can't just unrust it. That change is pretty much permanent.
And that irreversible change, that's what we call a chemical reaction. It's a total transformation. You start with your ingredients, which we call reactants, and they go through a process to become something completely new. We call those the products. Simple as that, really.
So how do we describe these reactions? Writing out carbon and oxygen get together to form carbon dioxide every single time would be a huge pain. That's where Section 2 comes in. We need a special language, a kind of chemical shorthand to be precise and efficient.
And that language is the chemical equation. Instead of using long, clunky sentences, we use symbols and formulas. Think of it as the official grammar of chemistry. It's clean, it's precise, and it's understood by scientists all over the world.
This is a perfect example. On the left side of that arrow, you have your reactants, C for carbon plus O2 for oxygen. The arrow itself just means yields or produces. And on the right side, you've got your brand new product, CO2, carbon dioxide. Reactants on the left, products on the right. Easy peasy.
Now, for a super important part, Section 3, balancing the chemical books. This is crucial. Just like in accounting, everything has to add up. You can't just have atoms popping into existence or vanishing into thin air. That's not how the universe works.
Which, of course, leads to the big question, why? Why is this so important? What fundamental rule are we actually following here?
And the answer is one of the biggest rules in all of science, the law of conservation of mass. All it says is that matter can't be created or destroyed. In a chemical reaction, all the atoms are just getting rearranged. So that means the number of atoms for each element has to be exactly the same on both sides of that arrow, no exceptions.
Let's look at this example right here. This table is an atom inventory for the reaction of iron and water. See the problem? On the reactant side, we start with just 1 iron atom, but on the product side, we magically have 3. And we start with 1 oxygen atom and somehow end up with 4. The scales are totally out of whack. This equation, as it's written now, is breaking a fundamental law of physics. We've got to fix it.
So how do we do it? Well, we add numbers called coefficients in front of the molecules until everything balances out. There's a method to the madness. A good rule of thumb is to start with the most complicated-looking element, in this case, the oxygen. Then we move on to the iron. And finally, we tackle the hydrogen, which usually just falls into place by the end.
And voila! Here is the balanced equation. By adding those coefficients, we now have a perfect balance. Let's do a quick count. 3 iron atoms on the left, 3 on the right. Check. 8 hydrogen atoms on the left, that's 4 times 2, and 8 on the right. Check. And 4 oxygen atoms on the left and 4 on the right. Perfect. The books are balanced. The law of conservation of mass is happy.
Fantastic. Now that we know how to write and balance equations, let's explore their different personalities, if you will. Welcome to Section 4, the 6 types of reactions. Because, not all chemical reactions behave in the same way.
Here's a quick rundown of the main players we're going to meet. We've got combination, decomposition, displacement, and double displacement. Then there's oxidation and reduction. We usually just call that redox. And finally, reactions that are all about energy, exothermic and endothermic.
Let's start with 2 that are perfect opposites. On the left, combination. Think of this like construction. You take two or more simple things and build one more complex product. On the right, you have its opposite, decomposition. This is more like demolition. One big compound breaks down into its simpler pieces.
Next up, we have the dance-off. In a displacement reaction, one element basically cuts in and swaps places with another. But in a double displacement reaction, it's a full-on partner swap. The two compounds totally exchange parts to form two brand new compounds. It's like everyone on the dance floor switching partners at the same time.
Now for a really important pair, oxidation and reduction. The best way to think of them is as two sides of the same coin. Oxidation is when something loses electrons, while reduction is when something gains electrons. The key thing is, one can't happen without the other. That's why we lump them together and just call it a redox reaction.
And finally, let's talk energy. Exothermic reactions are the ones that release energy, usually as heat. Think about a campfire. It feels hot because that burning wood is an exothermic process. Endothermic reactions do the exact opposite. They actually absorb heat from their surroundings, which makes things feel cold.
Okay, we've covered a ton of theory. Let's bring it all back home in our final section, chemistry in our daily lives. Where do we actually see this stuff? The answer? Oh, just about everywhere.
Remember that redox reaction we were just talking about? Well, two of its most famous, or infamous, effects are corrosion and rancidity. Corrosion is that slow oxidation that destroys metals, like rust forming on your bike. And rancidity, that's the oxidation of fats and oils that makes your food, especially things like chips, taste stale and just gross.
And speaking of chips, this brings up a great question. You know how you open a bag of chips and it feels like it's half full of air? Well, it's not just a sneaky way to give you fewer chips. There's actually some really clever chemistry going on. Here's the secret. That's not air in the bag, it's nitrogen gas. Nitrogen is super unreactive, so they pump the bag full of it to push all the oxygen out. It basically acts as an antioxidant, like a little bodyguard for the chips, preventing that chemical reaction, rancidity, from ever getting started. It's what keeps them fresh and crispy. Pretty cool, huh? And that's our whirlwind tour. From the bread rising in your kitchen to the battery that's powering the device you're watching this on, chemical reactions are the invisible engines that drive our world. So, my final question to you is this. What other unseen chemical reactions can you spot happening all around you right now?